So I think when Karl Heinz was talking this morning, he mentioned that it was good to have a lot of variety, and I forget the exact words he used, but different approaches. And I think I represent something a little different than most people. I think we're attacking this problem from a different sort of business and operational perspective than most people are. I'm with a company called Numenta, which has been around for 9 years. There's a little bit of confusion of our naming. We've been changing it a bit. We've clarified. Let me just explain. Our structure is a little bit unusual. Numenta has a mission to be a catalyst for machine intelligence. And by that I mean we're trying to accelerate the adoption of basically cortical modeling as a form of machine intelligence. And we take the catalyst as something not like we're trying to do it all ourselves. We're trying to accelerate it and not get consumed in the reaction. We have 3 different things we do. We have a research section of our business where we do theory and algorithms. We implement those in software. As last year, we started an open source project called NewPick. And all of the algorithms, all the stuff I'm talking about today, you will be able to get the actual source code for most of it in the NewPick community. It's unusual in that most people companies create open source communities on sort of peripheral software. Ours is the core of our machine learning algorithms are in NewPick, and I'll describe that a bit. And then we're also building products based on these algorithms, and that's our first product is called Grock, and it's built on a cortical model, and it's for streaming analytics, and I'll talk a bit about that. Most of my talk will be about the research and the progress we've been making in cortical modeling, and then briefly about NewPick and a little bit about applications. I'm going to start with a story. A number of years ago when Bill Gates was still the CEO of Microsoft, he went to a grade school and he was taking questions. And one of the students asked him a question and said, "Mr. Gates, do you think it's ever possible to build another company as successful as Microsoft?" This is before Google. And, but you know, Bill's a really smart guy. And his answer was, he didn't hesitate. He said, yes. He says, if you can invent a breakthrough computers can learn, that is worth 10 Microsofts. And he wasn't just talking about, you know, some machine learning algorithms. He understood deeply that computers have been built on 60 or 70 years of the same basic programming paradigm, and that there's an entirely different way of building machines that are based on learning, and the primary example of that is the human brain, or Neocortex in general, and that machine intelligence is going to be not just another 60, 70 years, but even bigger, that there's a larger opportunity here than we've had in computing over the last 70 years, and I believe that as well, and I believe that for over 30 years. So that's what I've dedicated my work to do. I prefer to talk about machine intelligence as opposed to computers that learn and machine learning. I want to go for the whole thing. I want a whole theory of what intelligence is, how cortex works. My goal is not to build robots. My goal is not to build human-like machines, but it's to deeply understand how the cortex works and then build amazing, fantastic machines that work on those principles that we might not even think about as at all like us. Okay, if we're going to do that, then of course we have to answer the questions: what are the principles we use to build intelligent machines? What are the foundations and the substrates we're going to use? And then what will be the applications? And we need to think about near-term and long-term applications. We need near-term applications because we have to drive interest and get money and people excited about it. But we don't want to just solve near-term problems with clever engineering solutions. At least I don't. I want to work towards the long-term. I want to set the right architecture for the next 70 years. And so we have to think about long-term what our goals are as well. And I would rather take the more difficult path than solving a short-term problem, which tends to happen a lot of times to people. Now, you already know my answer to the first question, but I'm going to spend most of my talk talking about that. What are the principles we use to build intelligent machines? And, of course, I believe that those principles will be the ones of the neocortex. And, of course, we already heard just in the last speaker, we heard some commentary about this. The neocortex is about 80% of the volume of your brain, a human brain. It's where all high-level vision, language, and planning occurs. I'm very aware of, and we spend a lot of time discussing subcortical structures and how they interact with the cortex. I'm not going to talk about them today. This is short, I can only cover so much. But, you know, going for the core principles in the neocortex is what we're shooting for. There's a couple things I recommend it. These might be obvious, but they're worth stating again. It's an incredibly flexible system. It can learn practically anything. We don't know what its limits are yet. But we all learned how to design computers and how to sit in conference rooms and make coffee and drive cars and write software, and none of that we're under evolutionary pressure for. Incredible number of things. In fact, it gets as close to a universal learning machine as we can imagine. And it's interesting to think of the parallels going back to Turing in 1935 when he wrote about universal, we now call the universal Turing machine. And I think there's some parallels there. So this is an incredibly powerful system, and if we can figure out how it works, that would be great. The other major region it recommends in neocortex and brain-like structures, I'm sure everyone in this room knows, is an incredibly robust system. It's made of terribly unreliable elements at the neuron and the synapse level. They're dying. It's a messy configuration, yet it's very robust, and it runs very, very reliably. So those are things we need to do to get past Moore's law and other problems that you're all aware of. And then finally, I run into a lot of people who argue with me about this, and maybe not in this room, but a lot of people debate, like, well, what level of neurorealism do you have to do, and why do we have to pay attention to these details? I had this just 2 weeks ago at Jacob's workshop where people were arguing against this idea, that you really need to know the neuroscience. And I think you do. One of the things I just say to people, I said, look, if we really understood how the neocortex works, and you could understand it in detail, and it was all written down, no one would be arguing about whether we should be replicating that. They'd all be racing to do that. The only reason they don't today is they don't understand it, and so and most people don't know how to understand it, and most people think it's way too complicated to understand, so they run away from it. But I argue that, and I'm going to talk to you today, I think we're making tremendous progress on this, more so than most of you think or know about. And I'm very excited about it. I'm going to tell you about at least my view on that and the progress that we're making. Okay, I'm going to start off with some high-level concepts, which I hope you don't find it controversial. And I'm going to keep drilling down deeper and deeper, and it's going to get a little bit harder and harder, but won't go too deep. So starting at the very top level, what does the cortex do? It essentially takes streaming sensory data, and it builds a model of the world. To me, the retina is not a sense. The retina is a million sensors. It's a 2D array of a million sensors. The body senses, the somatosensory sensors are about another million bits coming out of the spinal cord. The cochlea, about 30,000 axons coming in from them. So you got a few million sensors are coming in, streaming, and the cortex has to learn from an online model of the world. And it builds a model, and from that model it can make predictions about the future. We're constantly making predictions. It can detect anomalies and take actions. And of course, by taking actions, the way I think about this is that most of the changes that occur on your sensory organs are occurring because of your own actions. Not all of them, but most of them, the vast majority. And so when I move my eyes, that's my moving in the world. I'm changing the innovation on my sensory organs when I touch this lectern, or even hearing myself. So there's a feedback loop that goes on here. So if we say what does the neocortex do, it learns a sensory motor model of the world, and we want to know how it does that exactly. We have an overall theory for this, which we call hierarchical temporal memory. And when I first started talking about this, it had more controversial to it, but now a lot of people think similar ideas. And I didn't invent this, but it's been around. The ideas have been around for a while. There's several components of hierarchical temporal memory. First is that the neocortex is designed as a hierarchy. Although it's this thin sheet of cells, and it looks similar everywhere, those regions are connected in the hierarchy, as Fellman, Van Essen, and others have pointed out. And the most amazing thing about this, which has been known for over 30 years, is that the regions are basically doing the same thing. The visual regions are doing the same thing as auditory regions, are doing the same thing as somatosensory regions, as motor regions, whatever you want to call it. And that constancy exists across different modalities and different levels in the hierarchy and across species. Now, there are variations, no doubt about it, but we're going to focus on the commonality first before we start figuring out what kind of clever tricks and variations we made on that theme. And so you have this hierarchy of regions that are basically all doing the same thing, which is an amazing discovery. Therefore, we just need to figure out what those guys are doing and how they work in a hierarchy. The second thing, and this is also, I think, gaining some traction in the world, is that the vast majority of the memory in the cortical regions is memory of sequences or time-based patterns or time-based transitions. And you can think about this both from an inference and a motor point of view. From an inference point of view, it's pretty obvious that auditory inference requires time-based patterns. You can't understand what I'm saying unless you hear the sounds in exact orders or very precise orders and timing through time. And the same thing with touch. You really can't feel anything until you move your hands over it. There's no static sensation. Vision is also primarily a temporal inference. It's almost, your eyes are moving, your body's moving 3 to 5 times a second. You have complete new innervations on your optic nerve. And yet, we see the world as stable. Yet we do have the ability to do spatial inference in vision in certain situations. But in my mind, that you can understand as a derivative of after you've learned how to do temporal inference in vision. And so it's way too much time has been spent on trying to do spatial inference in vision, and I think it's been a real disservice. It's all about time-based patterns. And of course, motor behavior is all time-based patterns too. My speech right now is basically replaying back memory sequences I have stored earlier. And I can give this speech again and again, and I say these words over and over again, but I'm recalling patterns. This is a huge amount of temporal data that I'm both inferring and recalling in the cortex. And that's why we call it temporal memory. And then the third major component of this, excuse me, I'm losing my voice a little bit, is that as you go up the hierarchy, you have temporal stability. This is both observed and it's theoretically important. Meaning that if you have a sequence of patterns, and it's like a melody, you're going to form a stable representation, like the name of the melody, and then that is passed to the next region, and then you have sequences of sequences and so on. So as you go up the hierarchy, you have more stable patterns. I'm getting a glass of water, thank you. It doesn't hurt. I just had a cold last week, and so this is what the remnant of it is. Thank you, Winfried. I hope you can hear me. The same thing happens when you're going back down the hierarchy. You take a high-level concept, stability at the top, and then as you move down the hierarchy, you unfold it into more complex sequences, and those sequences, elements become sequences and so on. And that's what I'm doing again right here. I'm basically saying, oh, talk about this concept, talk about that concept, but then it leads to thousands of muscle innervations happening in the order of tens of milliseconds, all being done by my neocortex right now. So this is the basic theory of hierarchical temporal memory. And what we've been trying to do is understand exactly how this is implemented in cortex and the layers themselves, and we're making good progress on that. If I just jump in and look at a region in the neocortex, 2.5 millimeters thick, typically in a human, and you'll see it's a very thin sheet of cells. It's remarkable how thin it is if you haven't seen one. And then if we zoom in a little further than that, it doesn't really matter what region this is. It's going to be the same thing pretty much everywhere. You'll see, the first thing you'll see under the microscope, the very first organizational structure you see is layers of cells. And we can debate how many layers there are, but there's basically 4 layers of cells. There's layers 2, 3, there's 5, 4, 5, and 6. And you can subdivide those, and then you can, sometimes we have striate layer 4 and so on. We're going to put that aside for the moment. But the layered structure is visible under the microscope. You can really see that under the right techniques. And if you jump in further, there's another common organizational technique, which is the column. And here I'm talking about the microcolumn. I'm not talking about the larger column. Microcolumn is a very narrow stream of cells, 30 to 50 microns wide, maybe 100, 120 cells, and it spans all the cortical layers. It doesn't go up to layer 1, which we typically refer to as an acellular layer, not many cells up there. And it's been a lot of speculation going back to Mountcastle, maybe even earlier, that this is the replicable motif, the cortical unit. It's certainly something that happens in ontology, and it's visible in many places. There's been a lot of controversy about this, but a lot of nice review papers have basically said, yes, there are cortical columns, they exist, and they have these properties. And one of the properties that cortical columns have is the cells in those columns tend to have the same, a very similar feed-forward response property. So we'll see line orientation similar and so on. So what I believe is going on here very strongly is that the way to think about this is that the cellular layer, not the cortical column, is the motif. It's the unit of cortical computation. And what actually is going on is that each layer is implementing a variation of a common learning algorithm. That common learning algorithm is a type of sequence memory, and I'll clarify exactly what I mean by this in a moment. But each of these guys is doing a variation on a theme. They all have cells with certain type of properties and certain type of connectivity, and then there's a lot of variety in how you hook them up. But they're basically all doing something pretty similar in their thing, and I think we understand what that algorithm is. The mini-column is essential. We now understand it has 2 roles. One role is it plays an important aspect in how the layers of cells learn sequences. I'm going to go into that. It has another role in how the layers communicate with each other, which I'm not going to cover today. I don't have time for that. But we have a theoretical framework for understanding how all these things play together, and we've implemented a lot of it, and it really works really nicely. I'm just going to talk first about the feed forward. You consider the two layers that are involved in feed forward, layer 4 and layer 2, 3. And let's just talk about what the classic canonical circuit here. You have input that generally people say just comes to layer 4. By the way, for the neuroscientists in the room, I know all the details that this is a simplification, but it's still useful to talk about it this way. People think about the primary input is this layer 4, and you think like in V1 it comes from the retina. But it was even mentioned this morning, turns out there's another huge input through the thalamus that comes into the cortex at the same time, and that's a motor function. Meaning, like, for example, if the superior colliculus, which moves your eyes, it has a copy of its motor command, also goes to the cortex. The cortex gets both sensory information and motor information from the rest of the body. This is a constant theme throughout cortex. And when I say sensory, if I have a higher region in the cortex, I may not be getting direct input from a sensor. I'm getting from a region below, but it's the same type of afferent feed-forward information. Now, what I'm going to argue here is that what's going on in layer 4 is it's learning a sensory motor transitions. There's a little picture. Look at the face. When you typically look at a face, you saccade and fixate on different parts of the face. And while you're doing this, the face seems stable to you. Now, if your brain didn't know how the eyes were moving, then it would look like the world is thrashing about, moving constantly all over the place. It's not like there's this picture shifting. It's a completely new innovation every time you fixate on a new place. But it seems stable to you. Now, the order in which you do this is not repeatable. It's not like I always go eye, nose, mouth, eye, nose, mouth. It's not a high order pattern. There's some structure to it. It's not totally random, but I can't just look at the sequence and say, oh, I know what's going on. And what I believe is going on in layer 4, and I think I know how it's doing it exactly, is that it's basically saying I'm going to take what I'm currently seeing plus the motor command, and I'm going to make a prediction what I'm going to see next. And if I can do that, I can model these transitions based on motor behavior. And you'll end up with a stable representation. In fact, that's the next thing that goes on. I mentioned in the theory of hierarchical temporal memory that we have this stability going up the hierarchy. We have this coalescing of time. I now believe that's actually happening between layers of cells. And so when you go from layer 4 to layer 3, which is the canonical projection, if that layer 4 is able to make predictions about what's going to happen next and correctly model the transitions, it's going to pass it up to layer 3. Layer 3 is going to have a stable representation. And if for whatever layer 4 can't predict, those are going to be transferred up. And so layer 4 is going to see layer 3 is going to see the remainders of what layer 4 couldn't understand, couldn't predict. And what layer 3 does is it does a high order sequence memory. And what I mean by high order, you can think about, here's two patterns, A, B, C, D, and X, B, C, Y. Now, what I want to do is if I learn those patterns, like little melodies or something like that, and if I showed you A, B, C, I want it to predict D. And if I showed you X, B, C, I want it to predict Y. That's a definition of a higher order sequence because I need to have context from further back in time. Now, after I've thought about this quite a bit, I've now come to believe these are the only two methods the cortex can use to build a model of time-changing streaming temporal data. It can build a model based on your own behavior, which is not a high-order sequence, but it's a motor sensory sequence I can predict. And if I can't do that, the only other thing I can do is look for repeatable sequences in time. And it does this over and over again as you go up the hierarchy, because then you feed this up. In fact, the next layer will build a stable representation of what layer 3 could predict, and so on. So that's the basic idea of what's going on in layer 4 and layer 3. I claim that these are universal inference steps. They apply to any sensory modality. These are nothing about vision or hearing or touch here. And I believe they're basically working on the same algorithm, which we think we understand. Layer 5 and layer 6 are much poorly understood in my perspective, but we do know they're basically feedback. You can, in a very simplification, we can say in layer 5 you find the cells that project subcortically that generate motor behavior. That's a fact. And so you can think of layer 5, at least one of the things it does is it is generating behavior. And if you think about behavior, no matter where it is in the cortex, it's going to be sequences. So it's playing back sequences, recalling motor sequences under certain conditions. That is a fact. Layer 6 has got sort of 3 different types of major cell types going on there, and I'm just going to say we'll just call it attention. It's also feedback down the hierarchy and a few other things, but let's think of attention. Most people think about attention as a type of motor behavior. You think of covert attention as a type of motor behavior. So we can think of layer 5 and 6 as sort of going down and generating behavior. Now I'm going to make a claim here, which some of you might object to, and I'll explain it. I'm going to claim that we understand very well how layer 3 works. And we've tested this for years now, over the last 3 or 4 years. We've actually embedded a commercial product. What do I mean I understand it? I mean I understand it well enough to build a software implementation that solves really difficult problems and I can build something valuable with it. It doesn't mean I understand everything that's going on in the neuroscience. I don't. But I know it well enough to get started and saying I have a basic model of it. It's doing basically what it's doing. I can prove that. I can show you all the attributes of it. We've just, actually it was only in the last 5 months ago, we figured out how layer 4 can be sort of a duplicate or a doppelganger of layer 3 and how it works in the sensory motor stuff. So I'm very confident it's going to work. We've just started implementing it, but there's still some questions, so I'm going to put it at 90% understood, meaning again 90% confidence that I can build something really practical with this. And then we have good ideas about layer 5, very few about layer 6 pieces, and so we're still kind of trying to strum through that. But I feel like we've got a framework, and these pieces are falling into place, and they're really working pretty well. Okay, so now we're going to ask the question. I'm going to talk about how does this work? What is a layer of neurons doing, and how does it actually do it? I'm going to talk about it in the context of high-order sequences only, and before I do that, I need to talk about 2 other things. I need to talk about sparse distributed representations, and I need to talk about neurons. And then I'll come back and tell you how that plays into how a layer of cells can do high-order sequence memory. So let's talk about sparse distributed representations. Briefly, the easiest way to understand them is to think about comparing them to in a computer. In a computer, we use dense representations, which are essentially, we take a word, 16, 32, 64 bits. We use all combinations of 1s and 0s, and so an example would be ASCII code. And if I look at the ASCII code, I can say, what do the bits mean in that code? And I say they mean nothing. There's no inherent meaning of those bits. It's an arbitrary assignment. This is how we do things in computers. In the brain, of course, we find sparse activations. Everywhere you look, there are a few cells that are relatively active and many, many cells, or relatively many cells that are relatively inactive. And there could be reasons for this from an energy conservation principle, but I'm telling you it's also essential for the information processing capabilities and how the cells work and how they communicate. And I will go out and say you will not be able to build machines without understanding these principles. So just recall what this means. To have a sparse distributed representation, and I'm going to talk about bits, and you can think about bits as just neurons at the moment, okay? You have bits, you're going to have at least several thousand to do anything interesting. We've tested that. You're going to have a small percentage of those being active, 1s, and most of them being 0s. So an example I typically use is 2,000 bits, of which 2% are active, or you have 41 bits, or you can say 40 active cells and 1,960 inactive cells. And the key here is that the cells have some sort of semantic meaning. That's learned in a brain. It's not assigned by anybody. It's learned, but it's relatively stable. And so when I want to form a representation, I can take the same 2,000 cells, and at one point in time, I'll activate 40 that represent this set of attributes, another 40. Another time, I'll activate the same set of cells and activate a different 40. So, for example, if I were to hand code, and I wouldn't do this, but if I were to hand code bits to represent parts of the letters of the alphabet, I'd have bits that say, does this letter have, is it a vowel or a consonant? Is it sound like A, E, I, or U? Does it have a hard sound, a soft sound, a fricative sound? How is it drawn? Is it ascenders, descenders, closed shape, and so on? Where is it in the alphabet? And I'd come up with a whole set of attributes for the letter, and I'd pick the top 40 which match the letter I'm trying to represent. Now, when you do this, and brains are doing this all the time, there's some really great properties that come out of it that you have to understand. First of all, if 2 representations share bits, or they share the same cells being active, it means they're sharing semantic meaning. They have something semantically similar about them. And this is not going to happen by chance. And even if in my little example here, where I had 2,000 bits and only 40 are active, just even having 10 in common is statistically extremely unlikely by chance. It wouldn't be by chance, but still. So we can just say even a modest overlap between 2 representations is meaningful. Semantically. And I can quickly say, oh, this is how they're similar and this is how they're different semantically. It's not stored someplace else. It's in the coding itself. The second thing the brains need to do is they need to store and recall patterns. They have to be able to say, okay, I'm going to remember this pattern, and now I want to recognize if it occurs again. And so the way we're going to do that is we're not going to store all 2,000 bits. We're just going to store the locations of the 1 bits. So this would be like a cell connecting to a bunch of other cells saying, if I see these guys active, I'm going to know that this pattern had occurred in the past. And so if in my example here, if I had 41 bits, I could store the locations of all 41 bits. And if I see those bits being 1, I know I have the right representation, because all the others are going to be 0. However, we can't do that. We can't store connections, or we can't store the locations of all the 1 bits. It's not possible. So what if I subsample? What if I said you could only store the locations of 10 of these bits out of the 40? And I said, okay, now I come along and I recognize a pattern has the same 10 bits in the same locations. I could say that's a match. And you might say, well, this could be an error because the other 30 bits could be wrong. True. It could be. Again, statistically very unlikely to happen. And if I did make that mistake, I'd be making mistake for something semantically very similar to the thing I stored. And that's actually an advantage. It's a form of generalization. All right, my last property, which it's going to use everywhere in our models, is this one of union. I can take some number of sparse representations, say 10 of them, and I can order them together. I mean, literally just activate all the cells in those at the same time. And so it's less sparse now. It's maybe 20% sparse about. And now I have this union. I can't undo that. I can't say, hey, what were the original 10? Not possible. But I can ask the question, here's a new pattern that comes in. And what is it one of the original 10? And I'm going to claim that if I find that that new pattern matches up with ones in the union, I'm going to be one of the original 10. And you could say, well, that could be a mistake. I could be matching the bits on different ones of those original patterns. It's true, I could. Again, statistically, extremely unlikely. And if I did, I would be matching for things that were semantically similar. We're going to use this property a lot. I won't explain it all, but when the brain makes predictions, it can predict multiple things at the same time. When a neuron is trying to recognize different, a neuron, I'm going to argue in a second, to recognize many, many different patterns, and we're basically forming a union. The synapses on a neuron are a union of all the patterns it's trying to recognize, and it doesn't get them confused. Okay, now I need to talk a little bit about neurons because I have a point of view about this. And here's a typical pyramidal cell, going back to Cajal. Everyone uses the same picture all the time. And we can break down the input to this cell. This cell will have typically 10,000 synapses on it. Let's say on average in the cortex. And they feed forward, to feed forward input to the cell, like in layer 4, for example, or any cell, is a few hundred. And they tend to be proximal to the cell body. There's no synapses no positive synapses on the excitatory synapses on the cell body. It's all on dendrites. But these define the classic receptive field. This is the feed-forward driver, sometimes people call it, the driving feedback. And there's a few hundred synapses there. The rest of the thousands are on more distal dendritic segments. Now, if you look at the dendrites, we now know that they're active. So if you look at a small section of dendritic tree, maybe 40 microns long, and it might have 40 to 60 spines on it. If maybe say 10 and 15, Paul Rhodes here educated me about this, maybe 15 of these guys become active at the same time, then within a few milliseconds, within a short distance, and this has been documented by many people, that the dendrite can generate a dendritic spike. That dendritic spike, if it reaches the cell body, does not cause the cell to fire. It causes the cell to be depolarized. It's not sufficient to create a spike. But in our models, depolarization is a very, very important part of the model. We can think of this as context. The cell is looking at other contexts trying to predict its own activity. And there's thousands of synapses out there. And any one of these things will depolarize. If I find the right pattern out there, it'll depolarize the cell. So this cell is basically saying, I'm trying to predict when I'm going to become active by depolarization. And by the way, because you're depolarized, you'll fire quicker than other guys. You can inhibit them and so on. And so a neuron actually is a collection of, in our models, and I believe this very strongly, it's actually learning to recognize dozens or hundreds of unique patterns that exist in the cells around it. And it's saying, I'm looking for hundreds of these specific patterns that if I see that, I'm going to make a prediction that I'm going to become active, and that's an important property. I don't think you can model real cortical models without these kind of two-stage neurons. Some people argue otherwise. I had this 2 weeks ago again in Washington, where people say, yeah, you don't need to model neurons this way. Just do it as a two-level neural network. It's not true. You can't do it that way because it requires a learning signal, a back action potential that has to go back into the dendrites. So you really can't do that. You've got to have models like this. You can't avoid it. Here's a picture of one of our simulated neurons that we use in our models, where we model the, you can see in the green dots there, the proximal synapses, and the blue dots are the dendritic segments. We don't have to model the morphology of the tree. We just consider them a collection of coincidence detectors. And we've been having good success with this model so far. Okay, now that's background material. Now we're going to talk about how you actually build a layer of cells to learn sequences. So take a bunch of these neurons, and let's make a sheet of cells, just one layer sheet of cells, two-dimensional sheet of cells, and we're going to put an input into them. And this is the distributed pattern coming in. These are patterns going onto the proximal dendrites. Each of these cells will get some depolarization, and some are going to fire first and then others. The ones that get the most input, that match the input the best, are going to fire first, and they will inhibit their neighbors. And so it's very simple to form sparse distributed representations this way, and it's simple to learn to form good ones. So I won't go into that further here, but this is a sparse distributed representation of a set of cells representing this input. Now, over time, these are going to change. As patterns are going on, they're constantly going to change. And this is what's going on in your auditory cortex right now. These things are going back and forth like this. And it's over a large distributed sheet of cells. And so we want to actually learn the transitions between these patterns. And we're going to use local rules to do that. Each cell becomes active at some point in time, about 2% of the time on average. And when it becomes active, it's going to look for cells that were nearby recently that were active. And it's going to form connections to them, and it's going to form them on its distal dendrites. That's what you see like in a layer 3. You see all these connections to other cells nearby. And so when a cell sees one of these patterns, it's going to predict, it's going to be depolarized. And so if I train a system like this on a set of patterns, and I put in a new pattern, you're going to get some cells being active, and you're going to get some cells being depolarized. Now, you can see there's more yellow cells here than red cells. Why there are more depolarized cells? Because if I train on, typically, I'll train on multiple transitions. So if I train on A followed by B, and A followed by C, and A followed by D, and I show you A, it's going to predict B, C, and D at the same time. This is the beginning of a temporal sequence memory. And, but it's got some problems and things I haven't told you about. One of the big problems I do want to talk about is it's not a high order memory. There's no way of having a state which tells me, what happened 3 steps ago or 5 steps ago and so on. How do I make this a high order transition memory? So how do I learn sequences like ABCD versus XBCY? And the answer to this is going to be MiniColumns. And I'm going to show you how this works, at least how I believe it works very strongly. So let's imagine I have, this is a teeny little illustration of cortex. A few little mini-columns, and at any point in time, what we're going to say is that when I have a feed-forward input, it's going to activate all the cells in the mini-column. They're all going to kind of fire at the same time, and there's lots of evidence that this happens. And now I'm looking at 4 sections in time. First at A, then B, then C, and D. And you see at each time there's a different set of mini-columns being active. Now, I don't have to guarantee they're unique, because there could be some overlap, but imagine I've got hundreds or dozens or hundreds of these columns becoming active. It doesn't really matter if I just pick them randomly to start with. These patterns won't overlap much at all. So there's a series of patterns, A, B, C, D, different columns being activated. Now if I showed you the same sequence, different sequence, X, B, C, Y, you see X is different than A, of course. B and C are the same, and Y is different than D. But I don't have the ability to predict Y in one case and predict D in the other case at the end after C. So what's going to go on here? This is before training. After we do training, you're going to start off the same. It's like the first note in the melody. And what you're going to happen in the next moment, you're going to get B. But after we've learned this transition, we're going to form B differently. We're going to pick a single cell or a few cells in the column to be active. But it's the same columns. So notice here, I've got B prime. B prime is the same columns, but now I have a more sparse representation in the column. Now this behavior has been observed experimentally. It's exactly what I'm talking about, but I don't think they had a theoretical framework to explain it. So I can continue on here. Here's C prime. Same columns, different, a unique set of cells. And here's D prime. I'm predicting a unique D at this point in time. If I showed you this, if I trained on the other pattern, X, B double prime, C double prime, and Y double prime, you'll see the B prime and B double prime, same columns, different cells in the columns. Therefore, I have a very unique pattern to represent B in different contexts. If you do the math, even if I just had 40 active columns, a very small number, I only had 10 cells per column, a very small number, then I have 10 to the 40th ways of representing the same input in different contexts. That's a huge number. I've come to understand that everything you've learned in the world, you think like melodies. You can play back many, many melodies. you have a unique representation in your brain for every note in every melody you've ever learned. And you have the unique representation for every word in every monologue you've learned. And you have a unique representation for every item in every sequence of patterns as you walk around the world. It's a huge capacity and allows you to build high-order sequence memory. And I believe this was just going on in the cortex. As I said, there's good biological evidence for it, and it's also theoretically very, very sound. We call this basic algorithm the cortical learning algorithm. We think of it as a cellular layer. I'm just going to tell you that what it does. I'm not going to prove it to you right now. But it basically converts an input to a sparse representation. It learns the transitions in those representations, and it makes predictions and detects anomalies. We can apply it to three different things. We've proven extensively we can apply it to high-order sequence inference, and I'm going to show you some examples of that, which I think is going on in layer, excuse me, I mislabeled this. That should be layer 3. High-order sequence inference is layer 3. Sensory motor inference, layer 4, I've now shown on paper, and we're starting to implement it, and I believe the same algorithm will work for high-order motor recall in layer 5. Same basic idea, same cells, same sort of dendritic structure, but depending on what inputs you provide and a few other things, you get to do these different things. Okay, it's got really some nice capabilities. It's an online learning system. You just keep feeding data. It learns continuously. I haven't shown that, but it does. It's very high capacity. We don't really know how to measure this yet, but even the smallest systems we've created seem to have millions of transitions they can learn. It works on simple and local learning rules. This is essential for guys who want to build hardware. We need to build sheets of these things, really large layers of cells, and you can't. But it has to work on local learning rules, and it does. There's no global learning rules other than there could be sort of dopamine type of stuff. And the rules are simple. Require a couple different types of inhibition, monosynaptic, disynaptic progression, and so on. It's naturally fault tolerant. There's nothing in it that's sensitive, and there's no sensitive parameters. We've built millions of these models by now, and they generally all work. You can make them better or worse by changing the parameters, but there's nothing critical or very sensitive about them. It's very, very robust. And I believe it's a building block of Neocortex, and I believe that it's going to be the building block of machine intelligence. And I think it's a good target for hardware implementation, so I'll come back to that in a moment. Okay, I'm switching gears now. I'm now going to talk about applications, how we're applying this, give you a flavor for what we can do with it. We have applied it first using this cortical learning algorithm for basically anomaly detection. What we do is we can take data coming off of machines. Right now we're focusing on servers. We take these metrics coming off machines. We get data every 5 minutes. It's streaming data stream. We run it through an encoder, which is sort of a model of the cochlea, gets a sparse distributed representation. We feed this into the CLA. The CLA learns all the sequences and spatial temporal patterns it can in the data, and it makes a prediction, and it can detect how predictable the system is. And we can then detect if the predictability changes. If it becomes more predictable, less predictable, and that gives us an anomaly. It says, this system has changed from what it has been in the recent past. We can do this for multiple metrics, and I'm just going to jump to the conclusion. We've got a product called Grock, which we just started. We put up on the Amazon Marketplace 2 weeks ago. We're going to launch it formally in March. But what it does is it allows you to monitor thousands of data streams. And the ones we're focusing on right now are Amazon AWS instances and services. So if you're an Amazon AWS user, which is a lot of companies do this, they use it for their cloud, you basically can stream this data to Grock. And what Grock does is it builds automated models. There's no human intervention involved here at all. There's a very generic algorithm. And then it starts saying, okay, of all the servers you've got, which ones are the most unusual right now compared to what they were recently? It doesn't know anything about what these servers are doing. It just says, has this thing changed? Because I have a model of what it's supposed to be like, a cortical model. Has it changed? Is it becoming more or less predictable? And what we can do is that we can rank your instances. So you might have hundreds of these instances, but we'll say, you know what, right now in the last day or the last hour, these are the ones that are most unusual. And then you can drill down into it, and so you can say, okay, click on what were the metrics which led you to this. So now I can see we built separate models for each metric under a particular server. And then you can click on one of those metrics and say, well, what was the actual data and you can do this all on your phone. It's all real time. It's very cool. And you can say, what was the data that actually led to that unusual state? I can't say the system is broken. I can just say it's different. It's unusual. It's behaving differently than it has recently in the last several weeks. It's continuously learning. So these models are online learning constantly, and it's continuously updating. So every 5 minutes, this data moves across the screen and so on. Now, I'll give you just an example why the cortical learning algorithm, why a cortical model makes a big difference here. This is really hard to do in other methods. Here's an anomaly. You can see this little red peak there, right? That's something that happened on this particular server, and it was on this networked in parameter. Now, I'm looking at, this is over the last week. This is 8 days of data I'm looking at right here. And so something happened several days ago. And if I zoom in and I look at the metric, this is the actual network in metric. You can see it's all blue thing there. It's all blobby because it's compressing a lot of data into one space. But I wanted to show this because you notice there's 2 big spikes there. And you say, well, why didn't Grock pick those spikes out as anomalies? Because Grock has seen them before. He says, every once in a while I get one of those spikes. That's not unusual. So I'm not going to, it's not a threshold-based thing. So it's not unusual. But if I zoom in now, I'm going to look at now the same data, but I'm looking at a day's worth of data. So 24 hours. I now see a little bit expanded out here. And you can see there's sort of a regular pattern going on in here in this parameter. But you can see where the red bar occurred, and you look right there. And right there you see there was something unusual happen. Now, Grock said this signal is so predictable that that little change is so unusual, I'm going to flag it. And it learned that and says, you know what, that's a very unlikely thing. I haven't seen anything like that before. It's very difficult to get a human to look at this stuff 24 hours a day trying to figure out what's going on like this. But this never gets tired of doing this. Now here's another signal at the bottom right where it's much less predictable. This is not a regular signal at all. It's spiky, 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 and you really can't predict it. But Grock can also detect when it's changed again. You can see there's a section there where it becomes less predictable still, or maybe more predictable. So it's basically, the value of this is it automates this whole process. It's online learning. It does something that's very difficult. I don't know any other techniques for doing this. And so, that's why we picked this space, because we think it's uniquely solved for this kind of cortical model. This technology can be applied to any kind of data, financial, manufacturing, web, sales, basically looking for through thousands of data streams, trying to find unusual things that are occurring. I'm going to talk about another application. This is coming from a company called Sept Systems in Austria. They do natural language processing. They read our white paper and we publish all this stuff, and they did something really clever. They took Wikipedia and they generated from that, they generated sparse distributed representations of words, proper nouns, and phrases. So, they originally said over 100,000, now they say millions, I don't know. But basically, any word or phrase you give it, it'll say it comes back with a sparse distributed representation. It has the properties I mentioned earlier. So it's sparse, the bits have semantic meaning, although you may not know what they are. And so you can do very clever things with this. So for example, you can take the sparse distributed representation for the word apple, and you can subtract out the sparse distributed representation for the word fruit. And you get a new sparse distributed representation, meaning literally if the bits in fruit are on an apple, you turn them off. And now you can say, what is that new representation closest to? What is its overlap the strongest with? And the answer is computer. You can do this on their website. You can play with these things. You say apple minus fruit equals computer. If you then ask what are the other most common things that are related to, these are other close matches. Macintosh, Microsoft, Mac, Linux, operating system. Interesting how apple minus fruit is now Macintosh, because Macintosh was specifically a fruit. But anyway, not anymore. We then did something, our VP of Engineering did something the last hackathon we did in the fall, which he said, let's train sequences of these sparse distributed representation words in the CLA and see what happens. So he did something very simple. I don't want to oversell this. He basically created 3-word sentences. Animal, and the first word is an animal, the second word is eats or likes, and the third word was what the animal likes or eats. So elephants eats grass and elephants like water, things like that. He trained it on, I think, like 50 or 70 sentences like this. And then what he did, he said, okay, I'm going to feed it a new one. And the system had never seen the word fox, ever. Now we have a representation for fox, and in theory, the representation for fox has bits similar to other animals because it's semantically overlapping in some ways that we don't know. Then we said fox eats, and we had the CLA predict what does it think the fox eat. And what does it mean? It's basically which cells were predicted to become active next. We take that prediction, we look it up and say what was the closest thing we could find in the 100,000 word dictionary, and the answer we got was rodent. Now that, to me, was an amazing thing. I'm not overselling this, but it was the first time we were using these principles, using a cortical layer, sparse distributed representations, showing the kind of generalization that can occur with these algorithms. So I want to review here, the whole thing was done unsupervised. It's both semantic, it's both lexical grammatics generalization, and I think there's a lot of applications for this, and so there's going to be an effort by Sept and others to turn this into commercial products. I think there's a lot of clever things you can do with that. I'd like to point out that these two applications, Grock and Sept, used the exact same code base. There wasn't a line of code change in these learning algorithms. And that code base was not designed to do either one of these. It was designed to model layer 3 cells in cortex. And so it sort of suggests that we're getting close to this universal learning algorithm. These are powerful tools that can be applied to lots of different things. Okay, now on to a few more slides. NewPick, which is our open source project, we created that last summer. It's got source code for all this code I was talking about here, the encoders, the cortical learning algorithm. It's the same source code tree that we use in our product, so you can see exactly what we're shipping. There's an active community there, people interested in machine intelligence, and I'm active on that mailing list as well. There's a lot of resources up there, and you can find all that at Memento.org. We're trying to build a community here from the software perspective about machine intelligence. Here's my goals for 2014. One is to do more research. We're starting to implement and test the layer 4 sensory motor inference I talked about. We want to reintroduce hierarchy. Today our systems are not hierarchical, although we think we know how to do that. And we need to publish this work in peer-reviewed journals, which we haven't done yet. It's documented on our website, but not in peer-reviewed journals. NewPick, we're going to grow that community. It's continually growing all the time, nice and slow, and we're going to support partners. We have a couple of partners like CEPT, also IBM, Aberdeen Labs. Winfried Wilk is here. He's working on a program investigating hardware implementations of these algorithms. And then on the Grock side, we want to, in addition to building a business, which I hope to do, we want to demonstrate commercial value for the CLA. This is important for attracting resources, and I think it's really important too from a hardware point of view. My goal here is to provide a target for you guys who want to build hardware. A few years from now, I want to have a big business built on these algorithms. And you can say, look, there's a big business there, and here's what they're doing in software. And if I can replicate, if I can model that in hardware, I will be able to sell into that market space. And that's my approach for figuring out what to do with neuromorphic hardware, is to provide you guys a target for something that's interesting and valuable to go after. And of course, we're going to explore new application areas. I thought I'd just point out right now, what are the limits of what we can do here, the limits of software. So today we model this stuff, the Grock and the CEPT models are all pretty much similar. We're basically modeling one layer, layer 3, no hierarchy. It's only 2,000 columns, 2,000 MiniColumns, about 64,000 neurons. Each of those neurons can have up to 128 segments per cell. Each segment can have up to 40 active synapses. Something else I didn't mention, we actually need to model the growth of synapses. It's not just the strength of synapses, it's the growth. So we have this concept of potential synapses, which is much more than the number of synapses you actually have active. It's not about just increasing weights. You need to form and deform synapses. We know brains do that now. We know they do it everywhere, and you need to do that, unfortunately, because from a hardware point of view, it makes things harder, but that has to be done. So we're modeling in software what I would consider about 1/1,000,000th the size of a human neocortex. We've spent a lot of time optimizing that, and we can do an inference training step in about 50 milliseconds. It varies between 20 and 80 depending on what the setup is, but about 50 milliseconds. We can build some pretty cool products on that, but I can't make them very large. I'm very constrained by this. So we need hardware for the usual reasons. We need it for speed, we need it for power, and we need it for volume. Right now we have pretty big servers running these things, and I can't sustain it. We got to get beyond this. I can build a big business with this stuff today, but I got to get beyond this. And so we're going to have to do this as a community, and you all know that already. All right, that's the end of my talk. Thank you very much. I think we're taking questions later, or no?
Maybe one or two quick questions.
Does anyone have a burning question you want to ask me? Some brave soul.
A question about the continuous learning capability.
Yes.
Why doesn't it eventually lose track of what is a pattern and isn't? Why doesn't it just get washed out by perpetual learning?
It does. We had two ways of implementing. I hope everyone heard the question. Basically, why doesn't previous learning get lost? There's two ways you can implement these systems. We had to make a fundamental decision up front. One is, do we have finite resources? We're doing this in software. Do we have finite resources? Do we have fixed resources? And we went with fixed resources because we figured that's what's going to that's what brains basically have, and then that's what hardware is going to have. So we might as well stick with that. And so we start with a certain number of cells and a certain number of columns, and you can't go beyond that. And each cell can only have so many dendritic segments and so So what happens is, as you train these systems and the memory starts filling up, you start forgetting things. And what you'll forget is the stuff you haven't seen in the longest time. So we have a concept called synapse permanence, which is not the same as weight. It's not weight. It's basically how strong is this synapse, how hard is it to forget. And a synapse that's just recently formed has very low permanence and can be easily forgotten. Something that's been repeated many times is high permanence. But essentially, the more you train the system, it starts forgetting or it starts generalizing. The other mechanism by which you might call failure occurs is that after you've trained it on things, it starts saying, you know what, these patterns are similar to ones I've seen before. I'm not going to differentiate them exactly the same. So it has a graceful degradation in both cases, but the system has to forget. And by the way, in all these online learning situations, you want it to forget. I don't want the server to remember what it was looking like 6 months ago. That's irrelevant. The software's changed, the configuration's changed. This is the problem with anomaly detection today, is that they don't adapt. So this is a desirable attribute to say, let's forget. I won't go through the exact mechanisms by which it happens, but it's very similar to the, it's STTB type of stuff. If a synapse doesn't contribute and its timing is off, it gets decremented and it gets forgotten. I hope I answered your question. Well, this gentleman was standing there, so.
So I think in one of your previous talks along these lines, you talk about, going from software to hardware, but we're still talking about potentially the cloud, but I think you also believe there's a role for putting this into embedded systems. And I'm curious as to what your thoughts are there and what do you see as the unique opportunity for doing this on an embedded platform versus in the cloud?
That's a good question. None of my comments were directed for, the hardware should go in the cloud. That's just a product. That's what we're just doing right now, okay? By the way, people want to put Grock in embedded systems too. We're just not doing that at the moment. I think it's going to be like the computer industry in general. Look at how microprocessors and computers went. We went from these big rooms computers, and we still have those big room computers. But then the whole microcontroller and the embedded processor world blossomed, and now we have computers embedded everywhere. The same thing's going to happen here. We're going to have some very large systems that are centralized, that we're really maximizing for performance and size and speed. But I think there's going to be a huge number of embedded systems. One of the things I've talked about in the past is that if you think about the cortical hierarchy, we have to have that hierarchy in our head. It all has to be there. It can't be anywhere else. But when we implement these things outside of biology, we don't have to follow that restriction. We can basically put parts of the hierarchy anywhere we want. We can embed parts of the hierarchy and distribute it throughout a factory or distribute it throughout a network of power stations or whatever it is we're trying to understand. And so you can have, each smart meter can have its own cortical model going on. This is where we want to go. We want every server to have this embedded in it. Anything that's basically a node of the Internet of Things should be modeling its own behavior. And so there'll be a push to have this distributed out into the world, but it's not binary. It's going to be a very kind of Wild West kind of place. But there's opportunities on all ends of the spectrum, just like there are in computers today. I think I'll take one more question, and then I want to make sure we don't get off time here.
Apparently, the dendritic substructure is very important for your model. How fine-grained is that in your current software implementation?
How fine-grained is the dendritic structure? I'll just try to walk through it again. We basically break it into 3 different zones: proximal, basal, distal, and apical. The apical and the basal distal, basically we just model it as a series of dendritic segments. We don't try to capture any of the morphology of branches or, there's a lot of, we don't do any of that. We basically say there's a set of dendritic segments, and they all essentially can generate a dendritic spike, and we assume that spike gets to the cell body. That's a simplification, but it's working for us now. Yeah. What's that?
3 elements.
3 elements? Well, we have dozens of, our model will have up to 128 dendritic segments, right? Each one, and that's just a number we picked out of a hat. It's not outrageous. If you look at a real neuron, I don't know how many, in real neurons it's messier than this, but we've abstracted to this. So we'll have like 128, there'll be a proximal dendritic segment, which we actually model as 1. Then we have many 100 or so distal dendritic segments, and in each of those you can have it recognize one or more patterns. You can overlay multiple patterns on them. So each dendritic segment could recognize, up to maybe 20 or 40 different patterns in the world. In biology, I don't think it's anywhere clearly nearly as simple as that. It's nearby dendritic segments could interact and plate and so on. But it seems to be working pretty well. So that's basically the model. 128 segments, one proximal, 128 distal. Each distal one can have up to 40 synapses, and each distal one has many potential synapses. And what I didn't show is we model the growth of synapses. That's how we do it. We have many potential synapses. So a dendritic segment may have thousands of or hundreds or thousands of potential synapses, and when we train, we're basically growing and then forming a synapse and then strengthening it by making it more permanent. And actually our synapses are binary. We haven't had a need to go beyond that, and real synapses are so noisy that I don't think any precision could be assumed. So we basically have a scalar growth from unconnected to almost connected to very, very permanent, but it's a binary weight. So that's sort of the whole structure. This I think is an area that needs a lot of exploration. All right, I'm going to end right there. Let's go to the next one. Thank you.